everyone, let's make a start. So today we're joined by Peter and Alec, and they're going to tell us all about their experiences with underwater simulators and a little bit about what we can do with them, how we can use them, those sort of things. Please help yourself to the bagels that are at the back of the room there, so you can just hop up at any time and get another bagel during the talk. And we'll have lots of time for questions at the end as well. So let's take it away. Can everyone please welcome Peter and Alec?
All right, I'll get us started. So I want to start off by talking about what we have been using SIMS for and the kind of tools that we would use, and then also talk about what we haven't been doing and what we don't really have expertise in, but what you might want to do with your AXV in general. So we kind of sit on the left-hand side here, where we're doing like a full integration test of the software before we actually deploy the vehicle. We're not doing anything like visual data set augmentation, like trying to build extra images for your deep learning models. And we're not trying to do computational fluid dynamics, as cool as that is. But if you are interested in those kind of things, there's some interesting tools that may be of use. We're going to talk about left-hand side and some of the tools. So I did up a bit of an analysis. This is definitely a very biased analysis, so just what I think about different tools, and some that you may have come across before. So you're probably familiar with Gazebo. That's kind of the out-of-the-box ROS one. And it's good because it's free and there's support, but in terms of marine environments, we found it quite limited for what we wanted to do. So we gave it a go for a little while and then abandoned it. We looked at other things like Coppelia Sim, which used to be called VREP. We didn't think that was particularly good for our use case. We also looked at UW Sim, which might have been good maybe like 8 years ago, but it was an abandoned project. So we didn't find it particularly useful either. And also it was very limited to just underwater, and we were looking for both the underwater and above water. We ended up landing on Unity, kind of mainly because we're familiar with it, but it's got a couple of other nice perks as well. If you've ever used Unity before, you'll know that there's an asset store. So a lot of people make their video games in Unity, and they decide that this particular feature would be useful for other video games, and so they sell that feature. One of the features we did use was someone made a real-time buoyancy system that we bought for like $30, and that was the baseline that we used for the buoyancy, and we added onto that some additional features for more realism. But really, that got us like 80% of the way to a nice buoyancy system for just $30. You get the same kind of thing in Unreal Engine as well, but it's something you really miss if you go with one of these other tools like Gazebo. The last one I wanted to put in here was the NVIDIA Omniverse. NVIDIA are putting a lot of money into their simulators at the moment because I guess they have a lot of money and they want you to buy their GPUs. So that tool is getting better, but in terms of marine environments, I don't think they're putting much thought into that. If you go with NVIDIA Omniverse, you'll find that they put a lot of focus into kind of warehouse robotics with nice, realistic, ray-traced visuals, meaning you need to buy a very expensive graphics card. But that can be a bit of a hurdle to get into. Yeah, Kirsty?
Why is DIY sometimes orange and sometimes red? You know how to DIY. And then say for the ROS 2 bridge, for the ROS 2 support, it's like orange and yellow.
Yes. So I'd say for UW Sim, maybe it's not too bad. I put it orange there because it's a bit out of date, so it's pretty old. For Unity, that was a bit of effort, but there's some nice libraries for it. For Unreal Engine, that is more effort than Unity because you have to muck around with the DDS settings to get that to properly work with ROS. And I don't actually know about Omniverse. That may be green. It might be okay. Yeah.
Can any of these simulator simulate the current, underwater current?
That would probably lie in the DIY section. So it's something you have to add yourself. Like we added currents to our Unity sim, and that was fairly easy, but it might be a bit more difficult on other ones. I don't think any of them out of the box do currents.
But ultimately, the difficulty of setting that up is largely based on exactly how fine a detail you want to represent the currents. If you're just interested in a single force that is applied over time, like that's just always a super easy thing to do in any physics engine. But when you want to get into modeling these sort of currents hitting other walls and that then causing other sort of eddies and whatnot, then you're talking like seriously difficult for simulation.
Yeah, cool. Well, I might move on. So I wondered, like, what we wanted to get across in this seminar was one of the things was you kind of have to choose your priorities. Ideally, you want nice physics visuals and all that to run in real time, even faster than real time. But realistically, that's not going to happen. You kind of have to choose one. We went with nice enough physics, and we tried to do a balance overall with some of our projects. But in other projects, you see we might skimp out on the visuals or the real-time update to get what we want. And when I say physics can be a bit of a problem, I'll go back to this slide. And you'll notice in terms of gazebo, I said it's poor, but with out of the box, but with a lot of work, it could be the best. It could outdo pretty much any of these, and I want to go into why that's the case. So if you think about when you're simulating your robot, you want your simulation time and your real time to be pretty much matched 1-to-1. So if 1 second's passed in your sim time, that also means in real time that's 1 second as well. If you want to run faster than real time, you might want one real time second to equal two simulated seconds. Now, if you use something like Unity, what happens is, since it's a game engine and they prioritize having a nice smooth frame rate over the physics, because the physics are kind of just there to enhance the gameplay, but people are going to complain if the visuals are choppy. Then what they do is they sacrifice the nice mapping between real time and your simulation time. So what they do is they'll render a frame, and they'll figure out that it took so many milliseconds to render a frame, and we should have calculated some physics updates while I was rendering the frame, but I was busy rendering the frame, so I'll just quickly catch up on that now. And what you'll see multiple physics update steps happen really quickly before it goes back to rendering a frame. Now, this can be a problem if you're trying to control the robot. If you have in the time that it's rendering a frame, your control code decides, okay, I need to turn right for 1/4 of a second, then all of a sudden the engine finishes rendering its frame and then quickly processes physics for 1/2 a second. Your control code wasn't able to respond, and you've now turned for a full 1/2 a second while it was quickly doing these. So this is a bit of a problem. We didn't really have a good solution for this. We just kind of dealt with it. And I was like, well, we can't go too much faster in real time, otherwise weird stuff will happen. You'll see if we tried to in the sim, the nice control, if you try and turn to a particular direction and it would overshoot all of the time. It's a similar problem in Unreal. However, they do it slightly differently. So instead of nice fixed physics updates, the physics delta time increases depending on how long it takes to render a frame. So if you're rendering, if you put too much time into rendering, then the quality of a physics simulation will go down. So yeah, in Gazebo, I believe it could be the best because it's happening independently, so it's happening on another thread. We would have loved to have Unity physics running on another thread and then rendering separately so we could get the nice control code, but that just really wasn't feasible. All right, another thing we wanted to get across was that it's best to just go with as much as you need for the project. You can spend ages on a really nice fancy sim, but if you can get away with a 2D sim, yeah, it'll save you a lot of time.
Yeah.
Do you want to?
I've talked this a bit. Probably I'll just talk to Pete's column. So this particular project was the Coral AUV project. So the idea is that we were attempting to follow the contours of a reef environment autonomously and detecting that reef as we went. So we didn't have any predefined map of this environment. And so we had to just, using whatever sensors which were attached to the Coral AUV, which were in our case, three ping sonars, so those are single beam sonars, and a forward-facing stereo camera and a down-facing stereo camera. Just using those sensors, can we follow the reef? Now, first of all, we wanted a proof of concept to sort of demonstrate and ideate on how precisely we would be storing the data about where the reef contours are, and then making decisions on those. And so we came up with a two-dimensional test environment, which would sort of simulate the sort of, you can imagine a cross-section of the reef, and allow us to just quickly ideate and turn around some ideas and send them off to Ames and see what they thought about the feasibility of running them in that way. And here's the sort of the final 2D, the final sort of 2D logic that we ended up with, which sort of brought together all of our ideas. And a lot of this translated very well into the 3D environment when we finally went ahead and started implementing that. So the idea here being, you want to try and simplify your scenario as much as you can to just the essence of what makes it difficult, in order to save a lot of time later on. Because we could have gone straight to 3D to do this sort of analysis, but it would have been, we would have ended up stuck in all sorts of other hurdles prior to even coming up to whether or not the ideas we were coming up with were good. So we actually went through many different attempts, and sort of it was a bit of a competition between us to try and keep outdoing each other in terms of how well we could get the contour following to work. And so eventually we had sort of a great amalgamation of all these ideas, which then fed into the final product.
I just want to note from that one, we actually did our own physics setup for that, so we could run it at much higher than real time, which was quite helpful, and we couldn't do otherwise. Me, okay. Yeah, so we wanted to talk about some of the, about using a pre-existing platform. So unless you've got a good team behind you to build nice robots, you're going to save a lot of time if you find a nice pre-existing platform with a lot of the mechanical issues sorted out for you. We'll get more into that a bit later about the Coral AUV, where we had more of an experimental design, and it cost us a lot of development time that we. Anyways, so we use the Ranger bot a lot, and we use the SurfB a lot. These are great because they're kind of in-house QT, and they're cheap. Move on to, all right, yeah, so to the Coral AUV project. So this was a great project, but there was a lot of untested components. And we were in charge of doing the software stack, and it was during COVID years, so we had very limited capability of actually going out to the reef and testing this robot. We only actually got out to test the robot once, and we were plagued with hardware issues. So we didn't actually get to test all of the software we wrote, which is a bit disappointing. So if you go with a custom robot, definitely be prepared to put extra effort into fixing miscellaneous problems. The trouble we had was the depth sensor failed in a bit of a unique way. It was giving us readings, but and at the correct rate, but the depths were erroneous. So we tested it in the simulator, but we never tested this specific fail mode. And the software didn't pick up that there was any problem and just kept going on as normal. But it was actually just burying itself into the sand and draining the battery.
Specifically, the robot thought that it was far into the sky because the depth reading was 17 meters above sea level.
Yeah.
Something like that.
In retrospect, it's like you should be able to tell that you're above the water, but we were just looking at the update rate. We're like, oh yeah, still give enough data, no problem.
In terms of failure condition, that's a doozy, by the way. Do plan for that, because returning to the surface when your robot thinks the surface is below it is a real problem. So consider alternatives and redundancies. And in fact, the solution for us was to spend a night on the ship, reprogramming it such that the coral AEV would use this sensor's depth, absolute pressure sensor, as its own, in case of its own, where its own had failed. So just having a redundant sensor in that case would have saved us a lot of time. And yeah, we spent a whole night. I think we went to bed long after midnight, and then woke up at 6 a.m. the next day to get going again. So yeah, quite an experience, but not one that I would recommend.
Yeah. All right. I'll probably pass it over to Alec to talk about this skill.
Yeah, so having seen the two-dimensional example, a lot of this will look very familiar, just with an extra dimension of pane. And I see a few of you would have seen this already. So this is our Coral AEV pilot app. This is what we were initially employed by QUT to make, at least as far as Matt Dunbavin goes, other than Rangerbot in the case of Pete earlier on. And the idea for this is that an operator can simply select roughly a region of reef that they may have scanned before, they may have not, and the robot shall autonomously reach the start of its path and then make its way underwater to a certain depth, and then once it's at that depth, just autonomously scan whatever reef it can find within the sort of radius of this selected region. So here we can see that the robot has reached its target position. It does so over the water so that it maintains GPS connectivity the whole time, or at least until the very last moment. And then it dives and sort of determines. So we can see here that the depth we want is where this visualization is. And that's sort of the big boon of custom simulators, is that you get access to whatever you want in terms of visualization, which can be very helpful for debugging your robot's very unique behaviors. But in this case, it has reached its target depth and is simply gaining information about the reef over time and then deciding which is the next point, which is most advantageous for following the path on the reef and least likely to get itself into harm. So, and in general, the ability to find different problem areas on this example reef data that we were given by AIMS just gave us an opportunity to test and retest against problem areas as we updated our algorithms. So we kept we kept a list of places within the reef that we thought, places and depths within the reef data that we had, which we thought would cause us problems in the future. We would consider them stuck spots for the robot. And we would, every time we made substantial changes to the algorithms on the robot, we would simply revisit those places in simulation and test against each one in turn. And as such, we ended up with an algorithm that was fairly robust to everything that we could find on this reef to throw at it. And this reef being some real multi-scan data from, or multi-beam sonar data from John Brewer. So yeah, I think that covers that one. Right, so that was a simulator made specifically for the purpose of that one project. The whole project was about 9 months long from our perspective, and that included the time to make the simulator, which was about 3 months. So it was just head to the ground, get going really fast. So we had very little time and we did what we could, but we didn't focus on anything like extensibility. We didn't focus on graphics to a significant extent, just so much as it was functional for the purposes of stereo vision. But later we were given another brief by DSTG. They wanted a completely generalized marine simulator for the purposes, for their own purposes, which were to be mysterious to us, and therefore we didn't know what kind of robots we could put in there, or we had to put in there. We didn't know what kind of environments they needed in there. So we had to make a fully general purpose simulator. Now this is very useful, but it's not a track that I recommend for the vast majority of projects, because it is an extremely time-intensive process making such a thing. And so we've given you the estimate of lots of time, which is about accurate. I think while the other simulator took us about 3 months to get going, this simulator took us probably 2 years to get to the point of where we were properly happy, or like 1.5 years to get to the point of using it, and then 2 years before we were really happy with it. But of course, it gives us the ability to do things like this, where we can load up any vehicles custom as specified in a Zacro format, URDF, and we can have multi-vehicle. We can do all sorts of things that are otherwise prohibitively expensive and difficult in the real world. And using this, we can test a whole bunch of scenarios which before going to the demo stage, and vastly expedite the process of getting from concept to finished software to tested to demo. So like the whole process, simulators can help you with every step all the way, including, but not limited to, determining what you need for your sensing capability. So something that we used this simulator for was testing.
Essentially, these next couple slides are like why you'd want to build the simulator. I know it's a lot of effort, but this is one of the nice to haves.
How realistic is the fluid simulation? The fluid mechanic, how realistic is it?
Yeah, it depends on specifically what you want to refer to. So for, yeah.
So we did a little bit of testing about how well this simulation goes against the real world data. And while it could get the similar profiles in you give in this much force and you get out a velocity, and the curves were similar, you'd have perhaps an error of 20 to 30% in velocities. And I think the reason for that is because we were simplifying the geometry quite a lot in order to run it in real time. That's one of the trade-offs we made. If you really want to get that really high accurate fluid dynamics, you have to go with a computational fluid dynamics method. So yeah, we were able to get 20 to 30% within real, but...
So do you model current in this simulator?
Yeah, we do a little bit of current modeling, yes. We model...
Force field or not uniform force field?
Yes, so we get a lot of, there's two currents in here. One is from the wave motion, and that is added to, we add a custom current as well. We were going to investigate running some kind of CFD over the scene, and then that would generate some kind of vector field over time, and that we could import into the sim. We did run out of time though, but that would have been definitely something that's viable that we could have done for more realistic. Here, this is just a demonstration of the, when you add in physics objects to the scene, you can go crazy, add whatever you want. We added a submarine, and we could use it. This is testing the acoustic communications and seeing how objects block communications and how we deal with that. So yeah, it's just nice to be able to move around the physics objects however you want in a simulator.
The main use case for this, and the use to which it was put by Professor Matt Dunbabin, was that in reef environments, you often end up with shallow waters, and you can end up with things called coral bommies that are interrupting your direct line of sight for your USBL communications. And so he needed to make sort of algorithms which would respond to the sort of, or given a sort of knowledge about where the bommies are, how best to have multiple vehicles operate in that environment and have them communicating and positioning themselves within line of sight so that you can actually get these get this communication through. But in our case, we just put a submarine in the way. What else? This probably goes to answering your questions somewhat about the realistics of the physics. So this is specifically for surface vessels. We had a lot of difficulties with the performance on at the interface between submarine and above water, and some of those issues persist to this day. But you can see that even given some of those challenges, you can get some pretty good results in terms of like the whole goal here is to have this platform here, which is where your cameras will be mounted, behaving as similarly as possible to how it would in a given sea state. And the only way to really get that is to have sort of a reasonable simulation of all the joints in between the water surface and the platform itself, as well as the buoyancy of the pontoons. So here's a use case to which I put this sim, which is developing an autonomous obstacle avoidance system for this vehicle, which is the REF-RAS 100. It's a vehicle favored by militaries because it can be launched from a torpedo tube, but it itself is used for long distance scanning using side scan sonars. So on this vehicle, they wanted to know, could I make a sort of generalized obstacle avoidance system which could adhere to the constraints of the vehicle? So this vehicle is not your 6 degree of freedom Ranger bot. It can only move forward and backwards, and its control is just based on some control surfaces, a stern plane and a rudder. So that gives you a lot of operational difficulties when you're trying to avoid obstacles. And so I had to develop a system which could take in these constraints and take in a given control methodology and then apply that well. So this same system, the same code, more or less runs for both this vehicle and the Coral AEV and the Ranger bot, despite the fact that they have different methods of control. And the other thing that I was able to develop with this simulator was determining exactly what the minimum sensing requirement for achieving this was to be. So in this case, the sensors which are fused into the obstacle avoidance system are the beams from the DVR, which are 4 ranging sonars, and a single beam 30-degree cone sonar mounted to the front of the vehicle. And I determined that was a sufficient amount of sensing information to get this vehicle to avoid obstacles given the constraints of the vehicle's movement. And you could get better. I also did a few tests with different kinds of arrangement of sonar. So one in particular being a multi-beam on the front, even if it was just a narrow plane. And you could get better results in terms of the accuracy of the grid. So you can see this grid gets quite high at the front, but eventually gets drawn down by the DVL's beams. But just this one cheap sensor was going to be sufficient. So being able to test sensors ahead of time is a huge boon for simulators, and it means that you can save yourself a lot of expensive remanufacturing of your robot, and also just a lot of time in having to test these sensors in the real world first. What's next?
Yeah. So this slide I chucked in here to hammer home a point of an earlier slide. So when we made Sage, we had access to the full high fidelity simulator, but we ended up making another 2D simulator because we found that was going to be easier to develop Sage than it would be to hook up to the full 3D environment and do all our testing.
Sage being our brand control system.
Oh, yes. So yeah, just wanted to hammer home the point that just get away with what you need for the task, and you'll save yourself a lot of time. Yeah, cool. All right, that's basically it. So,
I might need a hit refresh. I added a few more cheeky slides right there. Let's see if I can't get those. Yeah, so here's sort of like the final boss for our DSTG work, which was to sense. Yeah, I should probably use this. We were to sense this. We needed to be able to sense this wreck of an airplane that was downed in sort of between after World War II kind of era. So these were vehicles that are kind of similar to Spitfires. Can I get this link to open? Sweet. Unfortunately, it's Vimeo, so I can't embed it. So this wreck here is the one we were looking for. It's about 14 meters depth, and it lies in Jarvis Bay, which is very close to a naval base. So let's see if I can skip to the part with the water. There we go. So this is what we're looking for. And as you can see, it's quite overgrown with, come on, Vimeo. I think the scary music isn't actually the real soundscape, but you can see it's quite overgrown. It's very embedded in the sand. So there was some doubt, given that it's 14 meters down, as to whether or not we would be able to sense this from the surface. And so obviously, given that we had a simulator which is capable of simulating these kinds of environments and telling us whether or not it's even vaguely viable, if a sensing suite will be adequate for a given situation, we simulated it. So we created a rough model of this plane. We chucked it at 14 meters depth. We mounted a single beam sonar to a surf bee in our simulator, and we drove over, and we noted the response we got out of our sensor, and we found that we could just barely perceive it, and with enough signal processing, we could substantially perceive it, which gave us the ability to fully implement the system for detecting this particular this firefly using the surf bee on the surface. And as field trip time is an expensive thing, I had no time to test this in the field in any way, shape or form until demo day, when we were out in Jarvis Bay with DSTG. And here's the results I got. So here in Sage, you can see I've made some, we already knew roughly where the firefly was located. So I prepared a mission which would cross over the firefly many times, and another mission which would be on the other side of our ship, far away from the firefly. So we should expect many detections, many detections over in the former, and very few or no detections in the latter. There's a bit of a debris field, so yeah, it's a bit wishy-washy as to whether or not it's the case. But as you can see from this graph that I produced that night, we can see a heavy cluster of detections on the bottom right, which is over where the real firefly is. And you can see the blue dot amongst that graph is the actual sighted location as according to the New South Wales Department of Environment. And over here on the other side of our ship, very few detections. So it was actually a successful mission, despite the fact that it was the first attempt on demo day. So you can really get a lot of mileage out of a simulator if you know its constraints and you work within those constraints. Thanks for listening.
Okay, just Does anyone want to kick us off with a question?
So when you're trying, like, you want to simulate a new sensor, you have to build a model of this sensor before you implement it into your simulation. Like, how do you know what that model even looks like?
Fortunately, you're very lucky here in that a lot of manufacturers provide very good data sheets telling you how their sensors behave. And so you can use those data sheets to kind of give you an impression of the noises that the noise that is involved. In the case of, we also implemented the thrusters as well. So you can get data sheets on how much thrust they put out given certain inputs, and you can just put that into your model, make it a plugin for your simulator, and then off you go.
A lot of the times, the tools that you use have got useful functions like raycasting through the physics objects or rendering the scene, but using only the depth map. So you can kind of get a bit of an idea from the tools how you're going to implement the data sheet.
Thanks for the presentation, really great presentation. Question, a lot of simulation or simulating things properly can take a lot of time. Do you have any tips and tricks on how to get answers quickly?
When you say time, do you mean development time and building the simulator?
Yeah.
Okay, yeah.
My answer to that is do it improperly first, so that you get a sort of impression on if what you want to do is going to function at all. And then you can make budgetary decisions based on that information. It's a lot easier to put forward that you need more time for simulation if you already have confirmation that the basic premise of what you want to do is going to work, and that you just need to do additional validation before you start spending the big money to put together the machine, to put together the team, etc.
Yeah, I'd agree with that. Start with like a 2D sim, something simple, and just see how it goes. See if it's worth even continue along the path.
Yeah, everyone appreciates if a project's cancelled early because it's infeasible. Scarlett?
I work a lot in underwater vision. Are there simulators that are good enough quality that, you know, it would be worth simulating, detecting or segmenting, you know, corals? Or, yeah.
So we actually, one of the earlier simulators that I made, not shown here, we investigated whether or not we could use the images to train some of the neural networks. So I was working with Ferris at the time, and he was making the QUT detector. So I grabbed I tried two methods. I tried making a 3D model of the QUTs and putting it in, and I tried getting just images of the QUTs and trying to texture that to surfaces. And there, what Ferris said was that it's not useful for training the primary network, but it was useful when you run the data from the simulator through his network, and he was getting false positives. So he could use those frames to help reduce the false positive rate. I think for something, if you want to use it for training data, you're going to want to move to a different tool, such as Cinema 4D or Blender, where you can properly ray trace the whole scene, and you're not worried about the real-time rendering requirement of these things. Yeah.
Cool. Thanks, everybody. Yeah.
So you guys have done like a lot of work on simulators and a lot of different projects. Is any of that available for others to use if they had an interest in the future, or is all of that tied up into like the IP of those projects?
So during the last phase of our work with DSTG, Peter and I decided it would be really good to upgrade our simulator to be a bit more future-proof. So we were initially using largely ROS1 because that's what we used within QUT. And DSTG wanted to use ROS2, so we simultaneously made the system compatible with ROS2, but barely. And so it was kind of a pain to use in ROS2. So we decided it was a good time at the end of the project to develop a better ROS2 integration. And this is where I went off on the deep end and started working on the C# ROS2 client library, RCL2.net. And at that, eventually once that was sufficiently developed, because it pre-existed my involvement, but it was not sufficiently developed to run a simulator, So once I had implemented all the features of the RCL.NET client library to make it capable of running a simulator, I then went ahead and started implementing the features which we required on the simulator side to integrate with this. And then Peter got involved as well at that point. And together we made the whole sort of system compatible with ROS2. And during that process, I'm coming to the point. During that process, we decided it would be good to hive off all of the sort of defense technology. And unfortunately, this is a lot of the marine specific work. We hived off all the defense technology into one repository, and we kept a separate repository, which was our ROS2 integration for our simulator for specifically Unity engine. And as a result of this, we now have a separate library, which is just really easy to spin up Unity simulations as far as easy goes, as far as simulating in ROS2 goes. It's relatively easy to spin up Unity simulators, which can integrate with ROS really well. And so now, and at some point, we managed to get permission from DSTG and from QUT to release this on QCR, which we are still yet to do because we're kind of busy at work. But we just need to go through things with a fine-tooth comb and talk to legal, and then we should be able to release all that body of work onto the QCR GitHub, which I believe is the current intended destination for it, which then will make it a lot easier for everyone within QCR and anyone in the open source community to spin up such Unity-based ROS2 simulators. I think that's about all.
Technically, since it was a joint project between DSTG and QUT, the high fidelity simulator can be used for research inside QUT only. Jordan used it for his PhD. Yep.
Cool. Is that everything?
Yes.
Lovely. Thank you, everyone.
Maybe so a bit above water question. So if you wanted to simulate a sail, so for example a kite, what would be your simulator of choice? Or is there any publicly available simulator for a kite?
I would say that getting access to water and wind in the same simulator is a very niche use case in terms of the number of people who require such a simulator, like really require it. I have heard that some people, and I can't say who, I have heard that some people need such a thing, and our simulator does somewhat support air current as well, and it uses a very similar, in fact, what Peter did is he essentially copied the same functionality for the underwater buoyancy and just applied it with a lower density of fluid to the above water scenario. So it can be done. It just depends on exactly what level of fidelity you need.
So if you are interested, let's say, not necessarily to mix the two, but to focus on what happened in the air to the kite, is there
in terms of wing
in
physics?
terms of wind and in terms of, you would like, for example, if your aim is to control the kite,
Yeah.
is there a simulator that comes to mind that say, oh, you could test some idea with this simulator?
I'd probably, like, this one can do in a very limited, like this one can in a limited way. We did aerofoils, but not deformable aerofoils. That's not implemented here. If you wanted deformable, you'd probably have to go to computational fluid dynamics.
Yeah, that's right.
Yeah. I don't know of anything real time that would currently support.
But a fixed wing, you could do.
Yeah, this one does support fixed wing aerofoils, yeah.
Yeah, specifically, all of our fins within the simulator. So, for example, on the back of the Rinus 100 are treated as fixed wing aerofoils in our simulator.
But the other benefit of being underwater is that the fluid dynamics is it's challenging, but it's slower than in air. which gives you
less turbulence.
a bit more, less turbulence and more opportunity to get sort of a realistic effect in real time than would be possible in air. You'd have to probably make a lot more, just do a lot more modeling and assumptions in order to get to air vehicles working in real time.
You look at the one to learn physics, maybe like learning how to
Maybe one day.
like machine learning, having some real thing behave in the water and reading the sensors and then simulating it and trying to find a mapping between it or transform them.
But you touch on something that I would like to
Specifically note here, for the kind of simulators that we've been making, it's far better to get information about the real behavior and then tune the simulator to model that real behavior than it is to try and suggest what the real physical behavior is going to be directly from the simulator. And that's because you're making a lot of assumptions, you're simplifying a lot of things in order to get things working in real time. So it's easier to go the other way and get a good result than it is to try and get the simulator to be perfect and then use that to make assumptions on how the physical properties of the vehicle will behave.
Yeah, actually, on the Ranger bot, Matt Dunbabin spends a lot of time carving out the foam so it sits nicely in the water. And that's just something we can't model in the sim. So I just made a little function that's like, set the center of gravity to here, and it'll just figure out all of the physics required to do that. And then you don't have to bother carving foam into virtual robots.
As entertaining as that would be for one afternoon.
All right, we might leave it there, and of course you can still ask Peter and Alec your questions one-on-one, but can we please thank them one more time?